Hi folks, welcome to another episode of Maths with Gary. Today we are talking about integration with trigonometric substitution again. Now, we've discussed this previously and talked about the substitutions you make and the functions you get, but today I want to talk about the issue of once you've integrated your function and got an answer in terms of theta, how do you go back to x or t or whatever variable it was, but usually it's going to be x. And that's a really important issue, and quite often students submit a lot of solutions with answers like the integral is equal to the sine of a half times the inverse sec of theta on 2 and stuff like that. And it's got all these inverse trig functions in it, and it's really not very helpful. It's very hard to understand what's going on with the solution, the function, what's it going to look like at various x values and so on. It's also very inefficient to calculate because all those functions, if you call a computer program for them, they've got to make an external call, and it's not very efficient. So today what I want to do is talk about going back from an integral with theta in it, function with theta in it, the answer with theta, to an answer involving x. And so this is the sort of thing I'm talking about, and it's not very helpful. Now, sometimes you can't avoid that. So if you integrate something and you get I equals the integral of d theta, that becomes theta plus c. And you can't go back to something involving x without using an inverse trig function. So for example, if your substitution was x equals 4 sine theta, then sine theta is x over 4, theta is the inverse sine of x over 4. And so your final result is I equals the inverse sine of x over 4 plus a constant, and that's the best we can do. But what if your final integral was something like 4 sine 2 theta plus a constant, or 4 tan theta plus a constant, something like that? How do you go back to something involving x without using inverse trig functions? Excuse me. You need to go back to your original substitution and work out the sides of a right triangle like this one. Okay, so here's a right triangle. That's going to be our angle theta there, and we need at least 2 sides to be able to find the trigonometric function. So if you want to know what tan theta is, you need at least 2 sides of this triangle. If you want to know sine 2 theta, it's a little bit more complicated, but we will get there. The sides of this triangle are going to depend on your original substitution, and you will need to find one of them by Pythagoras theorem. So take a look at these examples and see if you can find the missing side by Pythagoras theorem. For example, suppose your substitution is x equals 3 sine theta. Then sine theta is x over 3. And so that tells us that the hypotenuse of the triangle is 3, and your opposite side is x. Okay, sine theta is x over 3. There we have it, x over 3. The missing side, and hopefully you're able to do that by Pythagoras theorem, that is the square root of 9 minus x squared. So now that I know all 3 sides, I can work out all the trig functions of that angle theta. Suppose your original substitution was x equals 4 tan theta. Tan theta is x over 4. And so we've got the adjacent side being 4 and the opposite side being x. So now the tangent of theta is x over 4. And hopefully you have got that, 16 plus x squared. What if our original substitution was x equals 5 sec theta? Sec, of course, is 1 over cos. 1 over cos is x over 5, so cos theta must be 5 over x. The hypotenuse is x and the adjacent side is 5. What is the opposite? I'll give you a couple of seconds to quickly think about that. And of course, the opposite side is the square root of x squared minus 25. Okay, so that's how to set up a triangle using your initial substitution as a guide for what the sides are. Excuse me. So that's fine, but how do we get an integral involving theta, or an answer? An answer is a better word, I think, involving theta to one involving x. And very simply, you replace the trig functions in the answer with their equivalent expressions using the sides of the triangle. Okay, so we're assuming here that you can actually integrate the function of theta to get the integral, the answer in terms of theta. And so this example is about using these triangles to find the trigonometric functions, sine theta, cos theta, tan theta, sec theta, cosec theta, cot theta, sine of 2 theta, because sometimes you'll get an integral that involves sine 2 theta or cos 2 theta or something. I'm only going to do sine 2 theta, cos 2 theta. You'll follow a similar procedure. You'll just use a different trig identity. For example, if we've got this triangle here, and we now know this side by using Pythagoras' theorem, can you find all of these trig functions? And so I would urge you at this point to pause this video for a bit and have a go at using this triangle to find all of these functions. Okay, so this would be a good time to pause, grab a pencil and paper, pen and paper, whatever you write with, and have a go at finding all of these trig functions. Okay, I'm not going to pause the recording. You should be pausing playback and have a look at that. But let's move right along. Sorry, I'm going to do the solutions in a moment. How about this one? Can you find all of the functions sine theta, cos theta, all the way up to sine 2 theta, these functions here, for this triangle? Again, you should pause the recording and take a look at that. Can you find all of those trig functions? There should be an angle theta there. Why is there no angle theta? That's really disappointing. I spent so much time doing these diagrams. That one was messed up, so I had to redo that this morning, and I've forgotten the theta. All right, what about this one? Here we go, our third example. We've got this triangle here, and this, of course, was a substitution of 5 sec theta. And so our cos theta is 5 over x. And that gives us this side. Can you figure out sine theta, cos theta, all the way up to cot theta and even sine 2 theta using this triangle? So again, pause the recording for a couple of minutes and have a shot at that. I, however, will, what happened there? I, however, will move right on to the solutions. And if you look back at the first one, our sine theta was x over 3. That makes cosec theta 3 over x. Now here's an error right here. Dear me. Okay, so I'm going to pause the recording. So I've obviously used the wrong triangle. So I'm just going to pause the recording for a minute and fix that up. Hold on. Okay, so sorry about that. This is a brand new resource that I prepared yesterday, and I haven't fully got all the bugs out of it. I did briefly discuss it last night, and you notice that I had this formula down the bottom right, but I hadn't completed all of them in the middle. My apologies. Okay, so we've got our cosine theta as the square root of 9 minus x squared on 3, and if we have a look at the diagram, there's the cosine that's adjacent over hypotenuse. And that will absolutely look like square root of 9 minus x squared on 3. Sec theta, of course, is just, you flip that. Tangent of theta is the opposite over the adjacent. Cot theta is, you just flip that. Here's an interesting one. Sine 2 theta there is, of course, a trig identity which says that the sine of 2 theta is 2 sine theta cos theta. And if you look at this triangle, any one of these triangles, there's nothing here about an angle 2 theta. And so we really need this identity 2 sine theta cos theta, because I can figure out sine theta from one of these, and I can figure out cos theta. And there's the sine theta, and there's the cos theta. And so when I multiply those together, I get this. Okay, so hopefully you got most of those. If you didn't get this last one, then I suggest that you now go back and have a look at the last two triangles. That one there, and that one there, and see if you can figure out the sine of 2 theta from those. So again, you might want to pause this recording and take a look at that. But I'm going to move right along. There's my second triangle. And again, the sine theta is going to be x over the square root of 16 plus x squared. Cosec theta, I'm going to flip that. Cos theta is this. And so the sec theta is, again, you just turn that upside down. Tan theta is x over 4. Cot theta is 4 on x. And again, sine 2 theta is 2 sine theta cos theta, which is one of these. So again, just simplify that. Why have I got the square root of 16 plus x squared? That should just be, because if I'm multiplying the square root by the square root, I just get, dear me. I just get 16 plus x squared. Okay, how about this one? Have I done that again? No, I don't think I have. Here we go. What about those trigonometric functions based on this triangle? Again, there's my sine theta, there's my cosec theta, cos theta, sec theta. There's the tangent of theta and the cot theta. And again, sine 2 theta, 2 sine theta cos theta equals this one. So I've got x and x on the bottom. That gives me x squared. Yep, beautiful. All right, so hopefully that wasn't too confusing, and that will help you return from trigonometric functions to functions involving x, or whatever your original variable was, whether it be t. It will usually be x, particularly in this course. Okay, so on that note, ladies and gentlemen, I hope that makes a bit more sense, and that will help you in your studies in mathematics. All right. Keep calm, carry on, and do maths. Have a good day. Bye.